Hello and welcome back to PC Retro Programmer. In the previous video we took a look at the complex numbers and the Mandelbrot set. We started with a square in the complex plane from real value -2 to +2 and imaginary value -2 to +2, and for each point C in that square we determined whether it was in the Mandelbrot set or not by applying the Mandelbrot set iteration over and over again, starting from the value z equals 0. And if that value z ever goes outside the circle of radius 2, we know that that point C was not in the Mandelbrot set. And then we decided to scale everything by a factor of 4 so that we could work with values in the range -0.5 to 0.5 instead of -2 to 2. And this is just because these values will be easier to store and work with on the computer. So we ended up with a modified iteration which allows us to do this, and so now we need to start with capital Z equals 0, and then we check whether Z ever goes outside the circle of radius 0.5. If it does, then our point capital C is a scaled version of a point which is not in the Mandelbrot set. In today's video we're going to begin our implementation of this program. I started off by implementing a skeleton of the Mandelbrot set program, which I've called mandel.asm, and it basically just implements the outer loop of the Mandelbrot set program. In this skeleton I haven't actually implemented the Mandelbrot set iteration yet. All it does is iterate over all the pixels on the screen and compute the starting value C in the complex numbers corresponding to each of those pixels. The program itself I've taken from hello.asm, and I've just modified it to first go into the VGA mode that we're going to be using, and then to do those loops to iterate over all the pixels on the screen. And I've also added some variables in the data segment. It turns out that we can't fit everything in registers in this program, so we need some external values to store data in. And I'll come back to the precise meaning of these two variables a little bit later. The program itself starts off the same way as hello.asm, just setting up the DS segment. And then we change into the VGA mode that we're going to be using. That's 13H. It's the 320 by 200 256 color mode. And nothing could be easier. We just use the BIOS interrupt 10H for this. And we use the set video mode function, which is function 0. So we put 0 in the AH register, and we put the mode that we want, 13H, in the AL register. So that's what these two lines of code accomplish. And then I've written out a description of what this program should do. This is good practice to put comments in so that when you come back to the code later, you can actually see what it was intended to do. The first thing I did is describe the original Mandelbrot set iteration and also the square from -2 to 2 in the real and imaginary directions. And then I talked about how we compute the color of the pixels in this square by counting how many iterations it takes to go outside the circle of radius 2. And of course, if it doesn't go outside the circle of radius 2, we'll just set the pixel to black. And then I talked about our modified iteration that we derived on the left-hand side of the screen there, and how this changes it so that we have values from -0.5 to 0.5 instead of -2 to 2. And of course we're going to be using 16-bit values, basically because we have 16-bit registers. Now the next thing that I do is register allocation, and it's always good to write this down at the start of any assembly language program. The first thing that I noted is when I square z in our Mandelbrot set iteration, there's a number of multipliers that are going to be occurring there, and these are going to be 16-bit values that we're multiplying, and the result of that on these CPUs is always going to go in DXAX. This is just a feature of the multiply instructions, that the result of these large multiplications always goes in DXAX. So I'm just going to reserve those registers for that. And of course we're going to be drawing pixels on the screen, so I'm going to need the offset in video memory of the current pixel that we're dealing with, and that's just going to go in the DI register. Now, every complex value that we deal with has got a real and imaginary part. For example, the starting value C for each pixel has a real and imaginary part, A and B, and so I'm going to put those in the registers BX and CX. And similarly, every iteration I'm going to get this value Z, which has got a real and imaginary part X and Y, and so I'm going to put those in the registers SI and BP. And if you check, you'll realize that we've used up all our registers now, so anything else we're going to need to put in variables. Now we certainly need to keep track of the number of iterations we've done. After all, we can't just keep iterating each point forever. We have to bomb out at some point, and so we need to count iterations. And I'm going to store the current iteration in the iter variable. We're not going to use more than 256 iterations, so it'll fit in a byte nicely. So if you look above, you'd see that I allocated a byte for the iter variable in the data segment. And I think we'll actually use a cutoff of 32 for the number of iterations that we're going to use. Now, the other thing that we need is a way of dealing with the fact that the screen is not square. So we want to draw our Mandelbrot set nice and square, and so this means that we need to have a blank region on the right hand side of our screen. We'll draw the Mandelbrot set on the left hand side, and so we need to keep track of where we have to stop drawing pixels on each line. And this will just be an offset in video RAM, and I'm going to put it in the end line variable, and being an offset it's going to be 16 bits. So if you look above, you'll see that end line was allocated to be a word, 16 bits, and I started off with the value 0, and that's the iter variable that I talked about for counting the iterations, and this is going to be just a byte, and I'll start that off with the value 0. So that's our register allocation and variables. The next thing that we have to worry about is the pixels themselves. These are also not square. So it turns out that in CGA, VGA and EGA, when you use the 320x200 mode, the pixels are actually a little bit taller than they are wide. In fact, they're in the ratio of 1 to 1.2. So if we want to draw a square on the screen and we want it to be as high as the screen is, so 200 scan lines, then we're actually going to need 1.2 times 200, which is 240 pixels in the horizontal direction. So this is actually a square. So now we need to compute how much we need to move in the real and imaginary directions when we move by 1 pixel in the horizontal or vertical direction. So in the horizontal direction, we've got 240 pixels across our square, and the square goes from minus 0.5 to 0.5, which is a total of 1. So each shift by a pixel is 1 divided by 240. Of course, we want this value in hexadecimal, so I used an online hexadecimal calculator, or you can use a binary calculator and then just convert it to hexadecimal yourself. But either way, you're going to get this value here. And in the y direction, again, the square has a width of 1 in the y direction, and there are 200 scan lines. So we need to shift by this much in the imaginary direction. And again, this is in hexadecimal. So now we come to the code itself. So let's take a look at that. Now, if we're going to be drawing pixels on the screen, we need to put bytes into video RAM, and for that we need a segment and an offset address. Now, for video memory on VGA, the segment address is A000. And so we're going to put that value into the ES segment register, which is what we'll use to keep track of the video RAM segment. And then we're going to address all of the pixels within that segment using the DI register. So the offset has to go into the DI register. And the first pixel we're going to draw is the upper left corner of the screen. and this has offset 0 within video RAM, so we put 0 into the DI register. And an easy way to set a register to 0 in assembly language is just to XOR it with itself. Now the next thing we need to do is to set up our value capital C, our complex value, corresponding to that point in the upper left corner of the screen. Now I decided to have the imaginary axis running down the screen instead of up the screen. This is pretty typical when you're dealing with screen coordinates. You normally have the y coordinates going in the increasing direction down the screen, and so in the same way I'm going to have my imaginary axis increasing going down the screen. And what that means is that that upper left corner of the screen has to be real part minus 0.5 and imaginary part minus 0.5 as well. Now in hexadecimal I can represent minus 0.5 using the value 8000 in hexadecimal. Now obviously there's got to be a decimal point in that value somewhere, but we can't put decimal points into registers, so you just think of these as the bits after the decimal point, or I really should be saying binary point, I guess. And so of course the A value is in the BX register and the B value is in the CX register, so I put that same value into both of those registers, and that sets up my initial complex value capital C. Now the next thing I need is where I have to stop drawing pixels on the current line. And so remember, we're going to draw 240 pixels across the screen, and then we're going to have 80 black pixels. That's just so that we can keep our Mandelbrot set square on the screen. And so I need to put the offset 240 into the end line variable to keep track of the offset where we stop drawing pixels on the current line. And notice that this 240 value here, that could fit into a byte or a word, and you need to tell the assembler whether you're writing a byte or a word into memory, and so you use word PTR in this case, since we really mean write the word 240 into this variable endline, which holds a word. Now we're all ready to go. All of our initial values are set up. It's time to do our big loop for iterating over all the pixels on the screen. And the way you do a loop in assembly language is you start with a label at the beginning of your loop. And so I've just called it pixel loop here. It could be anything you like. And a label in assembly language has a colon, and I always put my labels over on the left here like this, so I can find them easily. And when we get to the end of our loop, if we still have more iterations to do, it will jump back to this label. So that's what the label is for. It's the point that you jump back to. So that's how you do a loop in assembly language. You just keep jumping back to the same point and executing the same code through over and over. So we're not going to put the Mandelbrot set iteration in now. That'll come later. So I've just left some comments here for code that's got to be added at a later point. All we're going to do at the moment is just iterate over all the pixels on the screen. And this is particularly easy to do in VGA because all the pixels are one after the other in video RAM. So I just need to keep iterating by incrementing the offset within video RAM. And so it's just a single instruction inc.di. And so every iteration of this loop is going to move by 1 pixel in video memory. Now we have to worry about the fact that we're only drawing 240 pixels on each line, and then we need to skip 80 pixels. We'll just leave them black. And so we need some code to detect whether we've reached that end line offset. We need to know if our current offset in DI is equal to the value in that end line variable. And so for that we use the comparison instruction. We'll compare DI with the value in end line. Notice we don't need the word PTR here, and that's because DI is a 16-bit register, and it can tell that this is a 16-bit comparison. So no need to tell it that this is a word. Now, in order to make use of this comparison, all the flags will be set appropriately after the comparison is done. We use something called a conditional jump. And so this one is JE, jump if equal. And so basically if DI is equal to that end line variable, then it's going to jump off to another label I've called end of line. Notice you don't put the colon here because this is not the label itself. This is just telling you to jump to that label. That label is actually right down the end of the file, and I'll show you where that is in a moment. And I've got a little piece of code down there to deal with the case where we've reached that end line offset. And that's where we'll add 80 to our offset and adjust our value of C and so on. Now, once that's done and we've dealt with that case, it'll jump back up here again and keep going. And for that, I've added a little label here that it can jump back to. So I've called that next line. So that little piece of code down the bottom of the file, which I'll show you in a moment, will jump back to here when it's finished. Now, in between those is the code that's going to be executed if we're not at the end of the current line. So if this jump if equals falls through, and the two values are not equal, it'll just keep executing code down here. And there's only one line that it's going to need to do here, it's this one. And basically all we need to do at this point is just update our complex value capital C. And we've only moved 1 pixel to the right. We're not at the end of the line, so we're still moving across the current line. We've already incremented our offset, so the only thing remaining is to increment the real part of our value capital C. We're staying on the same line, so there's no need to change the imaginary part. And we already calculated above that 1 divided by 240 is this value 0.0111 in hexadecimal. So that is how we deal with changing our C value if we're not at the end of the current line. So now let's jump down to that end of line label that I talked about, and we'll look at the code that deals with the case where we are at that end line offset. So it's all the way down at the bottom of the file here, after the program finishes, in fact. And here's the end of line label that it jumps down to. And here's where we skip over 80 pixels. It's just a matter of adding 80 to the offset within video memory. And the pixels are already black, so we don't need to actually do anything here. And that'll jump to the start of the next line. Of course, we need to update our value C in this case as well. And here we're going to need to change the real and imaginary parts of capital C. We need to reset the real part back to minus 0.5, so that's this line. And then we need to change the imaginary part by that 1 on 200, and that's the value we computed above that we need to add for that. And then we need to adjust our end line variable. So this now needs to be the point on the next line where we need to stop drawing pixels. And to compute that, we just add 320. There's 320 bytes per scan line, and so we just add 320 to that offset, and that's now the same point on the next line. And once we're done, we jump back up to that next line label that I talked about earlier. So that's up here again. So that's basically the end of our loop, and all we really need to do now is check whether we're at the end or whether we still have more pixels to deal with. So there's 320 by 200 pixels on the screen in this video mode. That's a total of 64,000 pixels, and so we just need to check our offset and see whether it's reached 64,000. It's really that simple, and if it has, then we're done. So if not, then we need to jump back to the start of our pixel loop, which was up here. You remember that's our big loop iterating over all the pixels. So for this we use the jump if not equal to, because if we're not at offset 64,000 yet, we still have more pixels to go, and we have to jump back to the pixel loop label. So see that we have a big loop here. It's just going to keep executing all of the code between here and here over and over again until di equals 64,000. Then this jump if not equal will fall through, and it will finally deal with the end of our program. So to finish our program off, we just wait for a key press. That's just 0 function of interrupt 16H, and then we want to change back to text mode. We don't want to stay in graphics mode, and that's just mode 3. Again, we just use our interrupt 10H, and finally we terminate our program and return back to DOS, and that's just function 4CH of the DOS interrupt 21H, as we've seen before. And that's the end of our program, and of course here's that little piece of code that I showed you earlier to deal with the end of the line, and of course there's the end statement at the end of the file, and that's it. So let's actually save this and then run this code and just make sure it actually works so far. Of course it won't draw a Mandelbrot set at the moment, it won't draw anything, but at least we can check this code's working. And in the next video we'll actually fill in the Mandelbrot set iteration itself. So let's save this file. We'll assemble the file and link it, and when we run this it's going to go into the VGA mode. It's not going to display anything, but it'll iterate over all the pixels, and then when we press a key it's going to go back to DOS. So let's just make sure that's what happens. Into the VGA mode, back to DOS. Seems to be working okay. Of course this is just the outside loop of our final Mandelbrot set program. We still need to implement the Mandelbrot set iteration and obviously drawing pixels, which we'll deal with in the next video. But before we get there, I want to mention a problem that we're going to encounter in the next video so that there's time to think about it in between. The issue is that we need to detect when we overflow the range minus 0.5 to 0.5. Now there is an assembly language instruction for this, so that's not the difficulty. The problem is that we need to check whether our value z is overflowed, and this has come from z squared plus c. And it could happen that z squared overflows, but then it comes back into range again when we add the c. So we really need to know whether z squared plus c has overflowed, and we need to deal with z squared overflowing, but we can't just stop at that point. In other words, what we need to do is make sure that z squared doesn't overflow, and then check whether z squared plus c does. So the only way that we can really do this easily is to divide all of our values through by a further factor of 2 for most of the iteration. So they'll actually lie in the range minus 0.25 to 0.25. And then the z squared won't be able to overflow, and when we add the plus c and then scale back up again to the original range, then we can check whether the z squared plus c overflowed. So that's the way we're going to handle it, and it's a little bit of a technicality, but it does stop us from implementing a Mandelbrot set that looks correct if we don't handle it that way. So look out for that in the next video where we'll finally actually draw a Mandelbrot set on the screen.